I'll begin with a prayer. Heavenly Father, we thank you for this day. I thank you again for the opportunity we have just to meet together and study your creation. I pray that you give us understanding about Baker-Campbell-Hausdorff relation. I pray that we can successfully calculate another order. Amen. All right, so I'm hopeful. I don't know, this is, I think we can definitely get the 1/12 terms today. My question is, can we go beyond that? Or will we just go, oh no, this is why we don't go beyond that? I'm not sure yet. All right, so the thing we just got to, and I will state without proof, because we could go through the proof, but I think that it's better, our time is better spent on other things. I thought about it, so I'm just going to state it. And we did it enough yet last time that you should understand it. So you have x and y complex matrices. So these are n by n complex matrices. Where have you been all day? This marker is amazing.
That's a nice marker.
I needed you earlier today. Where were you? Oh well. Then ddt of the exponential, matrix exponential, of course, of x plus ty. Take that derivative. After it's done, put t equals to 0. That is in fact the same as calculating e to the x. All right, times I minus the exponential of minus the adjoint of x, little adjoint, divided by, add x of y, where, let's see here, this, right, is, you could understand this as basically being g of x acting on y, where g of, let's say, I don't know, I guess I can use a t fairly safely here, right? G of t, or maybe I should use z, that'd probably be better. G of z is equal to, it's kind of the exponential series, but not quite. It's got exponential coefficients, but shifted off by 1. So it's like z to the n plus 1 over n factorial, I believe, if I remember right. So let's see, that looks like, and we worked this out last time, it's like, oh, and I'm still not quite right. There's, it's alternating. It's a minus 1 to the n in there as well. Anyway, the power series for that is, I still don't have it right.
Would it be z to the n minus 1?
Yeah, I should just start at 0. It's just that.
That would be over n plus 1 factorial.
Yeah, that's what it is. I knew there's something off here. It's kind of like the exponential, but not quite. And so, okay, so then it's like 1 minus z over 2 factorial plus z squared over 3 factorial minus z cubed over 4 factorial, and so forth and so on. So when you write that, that's basically, that's the power series which defines the thing I just put in parentheses. Basically what we're saying is you take this series and you replace z with x, all right? And when you do so, well, that's not quite it either.
Would it be add x?
Oh man, yeah, I'm still wrong. It's add x, right? Thank you. Still not right. G of add x, thank you. So like g of z was what? G of z was, how was it defined before? I've already forgotten.
1 minus e to the minus z over z.
Oh, okay. 1 minus e to the minus z over z.
Mm-hmm.
Okay. All right. So there's that, and then also if you just more generally differentiate ddt of e to the x as a function of time, you get e to the x as the function of time, this stuff. In other words, again, just put the adjoint in the series and do so. Oh man, I'm now confused. Oh, and an x on not y, but what?
dx
Dx dt, yeah. Alright, so this is theorem 3.5 on page 70 and 71 and 72 of this very nice book, which again is Lie groups, Lie algebras, and representations, an elementary introduction. Never mind this part as we mentioned. Alright, so after all, we are mere undergraduates. We shouldn't be using graduate books, right? So it's forbidden. One of my chief frustrations, the linear algebra book I really want to use. The start of it. This is the second book in linear algebra. I'm like, there's a stupid paragraph one after that. I could use that book. I just have to add a little material to it, be good. But I know that paragraph being there forbids me from using it. So sad. If I could buy my own and tear out that page. Ooh.
But how would they would buy it?
I would buy it for them and censor it. Or I could just go with a big black marker and redact that sentence.
And they call more attention to it than otherwise.
That's why I should just cut out the page. That's right. Nothing an X-Acto knife can't fix. Now the proof of that's like 2 pages, and it again involves this trick of dividing and taking the, I mean he divides algebraically by m like this. Where was I? So he does this thing where he divides by m, then he takes the m power. We saw that before in something I don't know if I actually did it or if I just glossed over it. I might have just glossed over it also. But
That was before it was like with a limit.
he eventually gets around to taking the limit as well. But it's that same sneaky trick. Yeah. Okay, so anyway, we have this identity which we'll use. All right. So that brings us to section 3.4, which is the proof of the Baker-Campbell-Hausdorff relation. And I think we should go through the proof because going through the proof will help us make sense of the calculation which follows. So I think that is worth our effort. So let's do it. Here it is. Oh no, I've lost my wonderful marker. Oh well, I guess I'll use this one. So first of all, we define z of t to be the log of e to the x times e to the ty. And I believe this is for fixed complex matrices x and y, all right, n by n. And he also says for if x and y are sufficiently small, then z of t is defined for 0 less than t less than 1. So for x and y small, we have 0 less than or equal to t less than or equal to 1. You know, with z of t sensible, let's say, all right. Makes sense to talk about how large or small a matrix is because we have its norm, right? So we can measure how large or small it is in view of that. Now, so it follows then, of course, that e to the z, right, is equal to, I guess I should write the t dependence, it kind of matters. E to the z of t is equal to e to the x, there is no x dependence, and then e to the ty. So basically exponentiate both sides. All right. And then his next move here is to say that, now let's see if we can understand this, e to the minus, let's see, I'm going to drop the of t, okay, ddt, e to the z is equal to e to the x, e to the ty inverse, e to the x, e to the ty, all acting on y. So you guys will have to help me out. I think that is by, I mean, what's that coming from? I mean, that's e to the minus z, right?
Mm-hmm.
So that's the multiplicative inverse of the exponential of z. Fine, I got that. And then, oh, I think it's just differentiation, right?
Yeah.
So if I differentiate this with respect to t, e to the x is a constant, so it just pulls out, right? And then the derivative of e to the ty is just e to the ty times y. Yeah, okay, this is just, elementary matrix exponential stuff, nothing big here. Now these are inverses, right?
Mm-hmm.
So we're just left with what?
Y.
Yes, y. But on the other hand, what do we have?
Formula from the theorem of that. Second one.
Right, so in terms of z at least, right? So, yeah, so from the theorem above, we can also write that this is equal to, going from here to here, by theorem 3.5, we have y is equal to what? It's equal to e to the, how's it go? E to the z of t I minus e to the what? E minus the adjoint of z of t divided by the adjoint of z of t. All of that acting on what? dz dt, right? Right.
And is there any specific reason we're allowed to write e to the x, e to the ty as e to the x plus the ty? To use theorem 3.5?
No, we didn't do that though.
Did you?
No. We just
Using the
used
second part.
we used this part.
Oh, this is just the second part. Okay, I see. I thought you were using the first part.
No. And I, in fact, wouldn't be able to write that, generally speaking.
Right. There's also an e to the minus ct in front of that.
Oh.
What you wrote in blue is d dt of e to the z. There's also an e to the minus z in front.
Oh, yes, thank you. So those cancel, and you're just left with what? You've got I minus e to the adjoint minus the adjoint of z of t, right, divided by the adjoint of z of... I'm really getting tired writing this. All of that on dz dt is equal to what?
Y.
Equal to y. Where y and e to the z are related according to this relation back over here, right?
It's 4:00 p.m.
All right, so here's what he says. If x and y are small enough, z of t will also be small, so that I minus the exponential minus the adjoint divided by the adjoint of z of t will be close to the identity and thus invertible, and so you can solve for dz dt. So basically, we go from here, and I'll do it up here. We can solve for dz dt equal to, this thing. And I guess at this point, it's like, that's great, but how in the world is that helpful, right? It's like, yeah, yay, okay, wonderful, that's, yeah, and how's that any better? Well, I don't know yet. All right. What I know is that most of the things we've talked about in the last several weeks get involved in this argument. It's got all the major players coming into play here. So, next thing he does is he feeds the definition of e to the z, or, well, the next step past the definition, the one I circled in blue there, he feeds that to the adjoint. All right, so if we take the group adjoint of that, what do we get? Come on. So this gives me the adjoint of e to the z of t is equal to the adjoint of e to the x times the adjoint of e to the ty. All right, that follows from the group homomorphism property of big add. But we also know that we have a relationship between the, there's a relationship between the little add and the big add in terms of how it filters through the exponential, right? I think I can erase this line at this point. I don't think we're going to need that now. I think we'll be okay if I erase it. I may regret this, but anyway, I'll leave that one for good measure. So what's that then?
E to the little I is big add.
E to the little. So this converts to what? E to the little add of z of t equals to what? Oh, what you just said.
Yeah.
So that's e to the
Sure.
little add of x, and that's e to the t times little add of y. Okay. And he's like, okay, but you can trade that for what? He says you could also write that in terms of log, right? It's the adjoint of z of t, right? Is log e to the add x, e to the t add y. If you like, you could write that instead. All right. Now what he says, he said plug this into 3.15. Now what's 3.15? 3.15 is this contraption up here. This guy is his 3.15. So he says you take plug what is, maybe this is the thing I last underlined. Let's see here. So he says combine this and that, and what happens?
E to the minus at z. T turns into. Cancel with the log, right?
Well, the minus matters though, right? I mean,
So we 1 over.
huh. Oh, sorry. I do have a book. I need to change color again. So here, I'll go back to black. So, come on. Get. All right. So, let's see if we can understand this next step. Well, I think he writes it rather he just writes it kind of like without too much simplification. dz dt is equal to curly bracket I minus e to the add x, e to the t add y, all of that inverse. And then, oh, it is just exactly what we said, isn't it? Yeah. And then downstairs you got log of e to the add x, e to the t add y. And all that x and y. All right, great. Now his next observation is that
There's also an inverse on the outside of the braces.
Oh, yes, thank you. Good point. So I think his next point is to observe that this g of z is also equal to, I'm going to go back up to the top of the board now. It's 1 minus 1 over z divided by log z all inverted. 1 minus 1 over z divided by log z all inverted. 1 minus 1 over z, 1 minus 1 over z divided by log of z all inverted. That is apparently equal to, that's what he says.
Interesting.
Just gotta believe it.
That's what it says.
Now, I'm not sure if that's, this may not be a reciprocal inverse though.
Yeah,
Okay?
it's a functional
So,
inverse.
this is equal to g inverse
Yeah.
of z, let's say, okay. No, not that kind of, this kind of equality, all right? I mean, you can try that out pretty fast, right? At least, well, gee, we can check one composition without too much work. Just plug this in the place of z, what do you get?
Z over minus z.
Seems like a headache. What? Really?
Not
What? Man. Am I doing it wrong? Yeah, I don't like my chances. You know?
Right.
That's not, or it's either, if it's that, it's hidden behind some kind of algebraic chicanery that's not apparent to me at the moment. Let me ponder these things. Oh. No, that's not what he says, though. He says g of z is equal to the... I really do think that's a reciprocal. Well, no, that can't be. He doesn't say... But that should imply that 1 minus 1 over z divided by log z is equal to the inverse of... What does that inverse mean? It's a question, right? It must be inverse as series. Like it's the reciprocal series. My guess. Let's try that on for size. How do you expand log z as a series? What is log z as a series? Can you guys tell me?
Said in section 2, it's some m equals 1 to infinity.
Mm-hmm.
Minus 1 to the m plus 1
Mm-hmm.
times z minus 1 to the m over m.
Z minus 1?
Yeah,
Oh.
I think that's how he defines it.
Oh, yeah, okay, fine. All right. Well,
Page
if I'm going to center
32.
it, I guess if I'm going to center things at 1, I have, so I've got 1 minus 1 over z. Let's see here. Divided by log z What's this equal? I don't know, man.
Well, it's z minus 1 over z log z.
Okay. Right, which is like z minus 1 divided by z times what?
That's so.
Yeah, that. So that's like 1. Right? M equals 1 is... Oh no, m equals 1 gives you what? Z minus 1, right? And then minus... I'm not sure if this is helpful, guys. I'm just playing with stuff here. Just may have nothing to do with what we're doing. And then what? That's Z. Oh, that's Z, that's Z, that's Z. That pesky, pesky Z. Golly. I mean, I can divide this, right? I mean, so, of course, this is really just 1 over z times what? 1 minus 1 half z minus 1 plus 1 over 3 z minus 1 cubed plus da da da, right?
Mm-hmm.
Which is 1 over z times 1 plus 1 half z minus 1 stuff, whatever. I've been doing long division in Calc 2 lately, so I know this. But this, on the other hand, is still not in the way it should be formulated. This seems irrelevant. I'm going to erase this.
What are we trying to get to with
Well,
that?
he has this, he claims, right? Here's what he writes. He writes that g of z, all right? He says g of z is equal to 1 minus, now he doesn't write 1 over z, just to be clear, he writes z inverse, all right? 1 minus z inverse divided by log z, and then he's got these curly brackets here, just in case I'm dumb. Now I'm just letting mathematical superstition enter in, as if those curly brackets mean something we don't know about. That's g of z, that's another formula for g of z, where I believe...
If you look lower in 3.5, I think he says it's the actual reciprocal.
3.5, where is that?
74. So it looks like it's
GZ.
actually the reciprocal.
Oh, you know what this is? Oh, how embarrassing. And stupid. Did you see G before in this section?
I thought so.
You did not.
It's not G.
I should have called this thing anything but G. This is like H or something else. This is another function. It's got nothing to do directly with G. I'm an idiot. This is just H of Z. Stop this tape. Let's start over. No, I'm just kidding. It's too far in.
G is the one that we defined last week.
Yeah, G is a different function. That's your familiarity with it. And that's why you bought into my incorrect labeling of G, because you thought I was making a connection, whereas I was not. It's a different G. All right. So that's actually just a one-line implication from the definition of G, which is that G is log of Z divided by 1 over Z, right? Like, yeah, okay, great. All right, sorry about that.
That explains why it didn't make any sense.
That's good. I mean, it's good that we didn't make sense of it. Then it would have been sadder if we could have made sense of it. I guess the point is that this is straight up what? This is...
G of e to the add x.
Okay, so that's G of e to the...
Add x, e to the t other one. Evaluated at y.
What's that? evaluated that way.
Oh, and evaluated it. Why isn't it?
I mean, it's in the last one as well.
Yeah, I'm sorry. I was just thinking why it wasn't dy dt, but it's not y dy dt because that's what we worked out to start it today. Before I started saying stupid things. All right, there we go. I didn't expect you to have something at liberty. Goodness. Hooligans. Who's messing with the door to my hobbit house? How dare they? Ah! Hobbit horse should pull.
It's supposed to be open so you can look inside.
Aha! So you're the.
Oh, that was like if it was me, it was like a week or two ago.
Yeah, I just haven't noticed. It has to be open so you can look inside.
Yeah, so you can see the doors.
Flowers.
Sorry. You want to see Dwalin, don't you?
I love the Hobbit house. It's the greatest Lego set. Anyway, okay, where were we? Wasting time. Yes, I'm sorry. We behave. Oh man, I got a smudge in my book. Oh no. Hate that. Alright, where was I? So we now have dz dt is equal to g of e to the add times e to the t add y, and but I guess the point is that's a formal argument because I mean, here's the formality of it is this is like we're reciprocating functions in the complex domain here, right? And what we're saying, and this is the formal aspect of it, is how do you know that the corresponding operator evaluations likewise invert? See, because this is no longer a function of complex domain. This is the same power series with operators stuck in it. So, you know, basic. But anyway, this formal calculation gives you an indication of what you can prove carefully. And if you go through the careful calculation with the series, you can prove, in fact, this is true. And so then, he says it's not hard to show. I will take him for his word. And so now what you do then is just integrate this thing from 0 to 1. So we integrate dz dt from 0 to 1, and that's equal to the integral of g of the e to the add x, e to the t add y, acting on y, dt from 0 to 1. Right? Nothing really I can do about the right-hand side except cry. And the left-hand side, though, that's exactly z of 1 minus z of 0. But z of 0 is what?
1? No, it's x.
What is z of 0? That's a good question.
It's log of e to the x plus e, or times e to the 0.
Yeah, so
So log
c.
of
So it's just log of e to the x, which is x. Yeah.
Okay. So this is z of 1 minus x, right? Which is the Baker-Campbell-Hausdorff formula, almost. So we have c of 1 is equal to x plus that integral.
And z of 1 is log of e to the x, e to the y.
And you said z of 1 was, of course, log of, oh right, of course, e to the x is log of. So this is all basically kind of a, you know, a grown-up version of that integration by a parameter technique, right? I mean, you're after some identity for log of e to the x, e to the y. What do? You apparently introduce a parameter for t next to the y, e to the ty, and then you can differentiate it and use all this various sneaky business in order to derive that identity, which is known as the Baker. Well, this is a version of the Baker-Campbell-Hausdorff relation. It's not what I usually call the Baker-Campbell-Hausdorff relation by any means, but anyway, there it is. All right. Well, this was almost not in vain, because we do need to find a series much like it, but I'm going to have to erase that because it's not quite the series that I want. I prefer to work over here. I think I'm going to erase this stuff if you guys don't mind, because I think we're done with it.
Good.
But the reason I wanted to go through this particular calculation is it allows you to kind of see that the proof of the Baker-Campbell-Hausdorff, basically it's a combination of those, like divide by m, take the mth power, take the limit as m goes to infinity trick to get that derivative identity, which I haven't gone over explicitly in here. And also this, the big adjoint homomorphism property, the way the little adjoint homomorphism pairs together with it. It's got, there's a lot of machinery working together here to produce that Baker-Campbell-Hausdorff relation. Now, as I mentioned to you guys last time, there are proofs that are independent of this machinery. And if you want to see that, of course, you can look in naive Lie groups, or naive Lie theory, I guess it is, right? By Stilwell, where he has that proof by Eichler, which is like 3 pages of just brute force algebra, so-called Lie polynomials. And but I like the way we looked at it in this book, because it gives you a chance to start thinking about other things like these adjoint mappings, which take on a life of their own as you study Lie groups and the algebras more generally. Okay, so g of z is z log z divided by z minus 1. All right, now we got that. Now, that can be rewritten, all right? So to expand the z in power, so that's z minus 1 plus 1, right? That's my z, divided by z minus 1. And then we can expand the log z as what? As Daniel was just telling me, m equals 1 to infinity, minus 1 to the m plus 1, divided by m, z to the m, right? Z minus 1, rather, to the m. That is derivable from geometric series techniques in calculus 2, right? This is not a mysterious formula. This you can get from just basically adding 0, doing the differentiation, integrate the series, and it's like differentiate, integrate series to get power series for given functions in Calc 2. It's that business. Anyway, or you could just apply Taylor's theorem at 1 and get this, whatever. So the point is, this is what, z minus 1, parentheses, all right, minus 1/2, z minus 1 squared plus 1/3, z minus 1 cubed, and so forth. All right, so I'm going to rewrite this. I'm going to step away from this book for a second here and just calculate. So really you've got, I don't think this is helpful. I'd rather do it this way. This is 1 times the log of z, right? Oh, but I don't, that's not helpful to write it that way. It's 1 times just the series expansion for the log, right? That's not quite accurate yet. All right, I'll get it eventually. So this z minus 1 over z minus 1 is going to be 1. So I have sum. Sorry, I have trouble making choices lately. That's a problem. And my chief weakness is an inability to decide in mathematics. For example, if I had decided to use the word inner product in metric in a separate sense this semester in linear algebra, it would have been greatly helpful to the students. I'm going to start doing that, but man, it would have been much better if I'd been doing that all along. Oh well. It's not too late. So if you look at this, right? This, of course, we can rewrite this, right? I'm just going to rewrite it rather than writing it again because I'm tired of writing. So if I bring this inside, I get m minus 1, right?
Okay.
Great. And then one more step. So this is the sum minus 1 to the m plus 1 over m, z minus 1 to the m equals 1 to infinity. And let me change that m to a j. I don't know why, it just helps me. to make it my own. And then this I'm going to start, see this actually starts at 0 now, right? So I'm going to say j equals 1 to infinity, and here I'm going to let m minus 1 equal to j, all right? So with that adjustment, actually j would start where? J would start 0, right?
Yeah.
So I'm just throwing that term out. I'm going to put it at the start. J equals 0, and that sum is just what? It's, I mean, m equal to 1 is my j equal to 0, m equals to 1 is
So it's just 1.
just 1. Just peel that 1 out here. And then this is what? Minus 1 to the
J equals 2.
j plus 2?
Or just J.
Just j then, yeah. And then m is j plus 1. And then you got z minus 1 to the j. Okay, so there we go. We've got, and I'm going to, since we don't care about all this junk up here, I'm going to write it up here so we can keep working. All right. So what I just found is 1 plus what? Plus the sum. J equals 1 to infinity. And we have what? I can say minus 1 to the j times what? Times 1 over j plus 1, right?
Yeah, minus 1 over J.
And that's all times z minus 1 to the j. There you go. That's a cleaner thing. And I think we can simplify that further too by making a common denominator. What do you get?
Yeah.
Can I erase do? Do we have that? Do we have this right?
Yeah, we have that.
That's what you're saying?
So you get like negative 1 over J times J plus 1.
Yeah. Okay. So it's j. We said minus 1
Yeah.
over j times j plus 1.
Yeah.
So 1 plus the sum j equals 1 to infinity, and we'll just write minus 1 to the j plus 1 divided by j times j plus 1. So it's like we took a partial fractions problem and undid it in some sense. I mean, like a telescoping sum, right? But we untelescoped it. It's sort of, kind of, not quite, but anyway. Okay, well there it is. That's the explicit series formula. So we can expand, right, explicitly. Now, I don't know, I for some reason want to do it this way rather than term by term. It just makes me happy. So you can disagree with that if you want, but you'd be wrong. J equals 1, plus 1/2.
Yeah.
And then minus what?
1/6.
And then 1 over what?
12.
12? So we had 2 times 3, and now we got 3 times 4. Alright. I'm going to try to go to third order. He only has to second order in the book, alright?
I would do that. Me? Oh my goodness. What I'm doing right here? Yes. You love that
So now what do we do? I'm hoping we use the Baker-Campbell-Hausdorff formula to derive the Baker-Campbell-Hausdorff relations. I mean,
Love when he says he says meanwhile.
Part of my, what's that?
He says meanwhile.
Oh, meanwhile. It's like in Gotham City. Meanwhile, in Gotham City. Let's see here. No, I'm sorry. I don't know why I'm putting Gotham City into it, but let's see here. Where were we? So we're ultimately after this thing down here, right? G of the exponential of the adjoint. So this of that of y, right? So so let's write that out. E to the add x Where were we? That's the meanwhile. E to the t add y. Minus I. So the i's cancel. And, well, fine, I guess he doesn't write it that way, but. Sorry, we'll try not to be distracted by them. Okay, so this is I plus the adjoint of x plus 1/2 the adjoint of x squared plus 1/6 the adjoint of x cubed, right? And so forth. And then we've got I plus t times the adjoint of y plus 1/2 t squared adjoint of y squared plus 1/6 t cubed adjoint of y cubed, and so forth.
Minus I.
Yeah, I think the only thing I need down here is the final product, right? Well, anyway, it's all I'm keeping, so I hope it's all I need. All right. All right. Then what? So we can, yeah.
I'm still doing a minus I there.
Oh, yeah, that's kind of important, isn't it? Because if that didn't happen, this would be ever so much worse. Okay, so this is telling us what, I mean, well,
You sure you want to do it to the third?
not entirely sure. Why is he looking at minus, I'm sorry, I'm lost a little bit here. Why are we looking at product of the exponentials minus I?
So that because we have z minus 1 in the formula for g of z. Because we're eventually going to plug e to the add x, e to the t add y into g of z, right?
Well,
So in the formula we have g of
say again?
from the formula we have, the Baker-Campbell-Hausdorff, it's like it has g of e to the add x, e to the t add y,
Right.
So we're eventually going to plug it into what we have up there, which this series in terms of z minus 1.
Why in terms of z minus? Oh!
Right, to sum of powers of z minus 1.
Oh,
And
da
so
da 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 da.
we're
So.
gonna do powers of e to the add x, e to the t add y minus
Okay,
I.
so really, man, I guess I'd be happier. Okay, I see. It's because that g of z is not centered at 0, it's centered at 1, and correspondingly we were looking for what is the formula for the z, the quote-unquote z, which is the product of the exponential add x and e to the t add y.
Right, it's going to be centered at I.
Right, and we have to shift that by subtracting I. Okay, which is good because the i's cancel.
Yeah.
And we're just left with other things. I don't know why you guys are so afraid of it. It's just a little algebra.
I'm not scared.
You're not scared.
No, I want to do it.
You want to do it.
Yeah.
Yeah. Okay, there's the linear terms.
Yeah.
See, I can do it. Quadratic. I'll start with the 1/2.
X squared.
And then what else do we have?
That's t squared.
Oh, you want to get the
Oh, I guess we can get the middle one. We can get add x, t add y. Or,
Here, let me try to do things in a somewhat systematic order. I will start by what I'm going to do is I'm going to go from here across until I exhaust possible products that are of quadratic order and adjoints. So like, there it is. 1/2 t squared add y squared. And then this over here. Of course, there's a lazier way of doing this. If you're really after doing this efficiently, you'd look ahead a step and realize that you're taking y of this thing, right? So anything that has a naked adjoint of y sitting there is 0 anyway, because that gives you like commutator yy, which is 0. So pretty much this is 0, this is 0, this is 0. That's the only thing that matters so far. But anyway, I'm just going to keep doing it like this for now, until I get tired of it. Is there anything else, second order?
Yeah, 1/2
add
add
x
x.
All right, and then what's the third order stuff?
1/6 t cubed add y cubed.
And let's take the wisdom of what I just said and actually put it into practice. Let's ignore things which are going to
That have add y in them.
that have add y as their final, not in them, but if add y is the final thing in them. Is that it? That
What do you
doesn't
mean
seem. That
the-
seems too easy.
But then it would just be 1/6 add x cubed.
Yeah, right.
And that would be the only one to worry about.
That must not. I must be oversimplifying this a tad. Oh, I guess we still have to take this, right? I'm getting too carried away. And I can't throw them away yet. Where I could throw them away logically would be when I put them into
yeah,
this series up here. That's the point at which I can logically. If I try to do it too far ahead, I will get confused.
Yeah.
So let's not do that. I'm already confused enough already today. So 1/6 t cubed add cubed, and then what do you tell me?
1/2 add x t squared.
T squared add x
Add y squared.
add y squared, and plus what?
Plus
1.
1/2 add x squared. Or 1/2 t add x squared add y. Plus 1/6 add x cubed.
Is that add y?
Yeah, add y.
Add y.
And then plus what?
1/6 add x cubed.
Okay, I'm content with that. This is going to play the role of z minus 1. Right? Morally, that's what it's doing.
Morally.
Yes. I mean, that's not the other use of the word moral. Let's see here. Okay, so then what?
Now is g of, we find g of e to the add x. E to the add y.
So now we just have to.
And we should just look at the different powers.
Yeah, that's probably wise. So I'll start with the easy part 1. X on y. It gives us y. Yeah. Okay. Got that. 0. First. Let's see here. We got. See, we're saying,
So it's 1/2 z minus 1, right?
right? Now that's the only thing that will be, the only thing that matters. And of the z minus 1 terms, you only keep the first order, which would be, I'll write it all out here this time, add x of y. I mean, it's this acting on y, okay? Let me put some quotes there, but if you'd like, I can come up with some other fangled name for that, but I'm just going to leave it like that. I think it makes sense. And then that plus t. I mean, if you don't know about the properties of the adjoint or how the commutator works, You might have hope that that would be something, but of course we know it's nothing. So we're just left with, I think I'm still missing my what?
1/2.
Yeah. So there you go, 1/2 commutator of x and y.
Wait, why is there nothing else? If z minus 1 is all of that.
Because we're only looking to first order in commutators.
Wait, where?
I'm collecting all of the things in here that involve just one commutator. See, z minus, so that's the, and you can do that, logically you can do that. There's this stacking of orders of nested commutators, right? That's part of the point of this calculation, is there is no constant term here, right? So when you look at formally what z minus 1 squared is, this only has commutators of commutators and higher things. And higher things. And this has commutators of commutators of commutators and higher things. But we can what we're doing is we're just looking for no commutators, just one commutator in the formula, and next will be just two commutators in the formula.
Okay.
And we
Right.
can,
Oh, got it, yeah.
And we can get all of those by just looking up to here.
Okay, yeah.
I would point out that once you're comfortable with this way of thinking, this is way faster than what we did the other day. I know we're struggling with like getting used to this at the moment, but once you're used to it, think about how much faster this is than like all that series stuff we did the other day. I mean, it really is. You can start to see. I mean, I don't know, maybe I'm overselling it in a second. Second order, we'd have to look at, 1/2 z minus 1, and then minus 1/6 z minus 1 squared. Look for commutators of second order in there. Okay, so let's see here. The z minus 1, we pick up what? Now, at this point, I keep forgetting. We're taking that and we're letting it act on y, right? So we don't really care about this term or this term. The only thing that matters to us is that one in the z minus 1, just plain. So, and I'm missing a calculation to do this. Okay. Okay, let me get back on. So 1/2 t x y.
Where did the t come from?
That is a very good question, and the answer is fall man. Okay, so yes, you're not yet. They're perfect bodies or perfect minds. Yeah, that should have been this term, which has no t. Yeah, thank you. Very good. Now I can't even read off second order commutator terms off of minus 1/6 z minus 1 squared yet because I have not calculated. Oh, awful. Z minus 1 squared.
Yeah.
I will now foolishly attempt to do such, but I will do so with a focus on what I care about. So, the best of, let's say, best of z minus 1 squared.
Greatest hits.
Greatest hits, that's right, that's it here. So if you think about squaring this in your mind, of course you've got add x squared, right?
Right.
And then you've got also t add y add x. You also have add x add y,
But you don't count that.
but that's dead to us, that's right. And
That it?
yeah, that's about it to second order. Let's do the third order while we're at it. So to third order, what do we got? Of course we've got